Now that we have a handle on what graphs are and what they're used for, we're going to start looking at some terminology and definitions for graphs. So before you do this, I strongly urge you to try to work on some of the activities on the called graph terminology. Those have some of the lead-ins, some of the motivations for where these definitions come from. You don't have to do it necessarily, but it might help you understand some of the motivations behind the definitions that we make. Anyway, when we actually get to the video, we're going to give some definitions, and then we're going to demonstrate these definitions on example graphs. So again, remember the definition of a graph is it is an ordered pair of sets. V is a set called the vertex set. E is a set of unordered pairs of elements of V called the edge set. And so, of course, what do these look like on a visual representation of a graph? Well, here's an example. Right? You have the vertices A, B, C, D, E, and F, and you have edges between some of the pairs of those vertices. So here are the vertices. Those are in red. Those are the letters. Here are the edges visually. Those are just the connectors between the vertices. So they tell us what the ordered pairs are. So for instance, there's an edge between A and B. That means AB is an edge. So given a pair of vertices, we may want to know, is there an edge between them? Is there not an edge between them? And not only that, how many vertices do they share an edge with? So if we have V and W are vertices, if they actually share an edge, we call that being adjacent. So V and W are adjacent if the pair of VW is an edge. Again, if V is a vertex, the degree of V is the number of vertices that V is adjacent to. So if we're looking at our good old graph there, the two red vertices with the red edge between them, A and C, are adjacent because they have an edge between them. But if we look at the two vertices A and D, those are not adjacent because there is no edge between A and D. If we look at the vertex C, we notice that it is adjacent to the vertices A, B, and D. That's three vertices. That tells us that the degree of C is 3. Now the concept of incidence is similar to adjacency, right? When we have adjacent, two vertices are adjacent, that's between two vertices. For incidence, that represents a relationship between a vertex and an edge, instead of two vertices like it is for adjacent vertices. So we say a vertex and an edge are incident if the vertex is part of that edge. So if we look here, the vertex C is incident to the edge, that red edge there between A and C. And so the vertex C and the edge AC are incident to one another. Now notice that we in the old days being like what, 1 minute ago, we talked about the degree of a vertex being the number of vertices that the vertex is adjacent to. Same thing. It could also be stated as the number of edges that is incident to. You see that vertex C has 3 edges coming out of it, one going to A, one going to B, one going to D. That's 3 edges. That is degree 3. A subgraph of a graph G is a graph that you can sort of find inside of G. So what we mean, to be more precise about it, if G is a graph, a subgraph of G is a graph whose vertices come from V and whose edges come from E. And so if V prime is contained in V, then this is a special subgraph. This is a subgraph induced by V prime, is the graph whose vertex set is V prime and whose edge set is all the edges between vertices and V prime that are possible. Note that in just a regular old subgraph, you may have a bunch of vertices. You don't have to include all the edges from the original graph unless you want to. So for instance, here's our original graph, right? Here's a perfectly good subgraph. Sure, we're missing 2 edges. We're missing the edge between C and D, and we're missing the edge between D and E, right? But that's totally okay for a subgraph. However, if we want the subgraph that is induced by the vertices A, C, D, E, and F, we have to include those 2 edges. But if we're just talking about a normal subgraph, we can include them or not include them. It doesn't matter. So there's a lot of applications from graphs, but some of the applications involve moving from one vertex to another. And some movements are, well, I call them more purposeful, but they have different requirements than other types of movements. But most of the time when we move from one vertex to the next, we're moving along an edge. So we're moving between adjacent vertices. So if G is a graph, we call a string of vertices v1, v2, v3, all the way up to vn a walk if each consecutive pair of vertices in the string is an edge. So for instance, v1, v2 is an edge, right? There's an edge between v1 and v2. There's an edge between v2 and v3, v3, v4, etc., all the way up to vn minus 1, vn. That's our last edge in that walk. And those are all edges. Note that we can repeat vertices and we can repeat edges. So for instance, v1 and v2, if those are adjacent, we can just go back and forth between v1 and v2 we want. That's a perfectly good walk. Now, it's a little bit different for what we call a path. A path is a walk that has no repeated vertices. So you can't just go back and forth between vertices. You can't repeat vertices. And therefore, since you can't repeat vertices, you also can't repeat edges as well. So that's more purposeful, right? You're going from the first vertex to the last vertex without doing any repeats. So let's look at some examples. So if we, in the above graph, if we want to do a walk, we can start at A. So I turned A blue to say we started there. We can go to C if we wanted to, and so that red indicates that we traveled along that red edge from A to C. We can go then to D, travel along another red edge to D. That one's now blue. And then we can go over to E. Now we can go back to D if we want. I turn the edge yellow to indicate we travel along that edge twice, and I turn the vertex D green to indicate we did that one twice. So I'm going to change colors as we go along. We can go back to C. That edge turned yellow, and that C turned green as well. And we can go to B, and then and that gives us a perfectly good walk, right? Now, if we want a path has to be more purposeful. Let's say we start at E. Then we can move over to D, we can move up to C, we can move over to A, and we can move over to B. Everything's fine for a path as long as we don't repeat any vertices. No vertices were repeated, no paths were repeated. Notice we didn't take the shortest path to B. The shortest path would have been to, when we got to C, not to go to A, but to go directly to B. But as long as we don't repeat any vertices, it's a perfectly good path. So as I sort of alluded to in the last bit of discussion, paths don't have to be the shortest way to travel between two vertices, right? There may be a lot of paths between two given vertices. For instance, I showed you one with the path that we did, but for instance, if we wanted a path between A and B, we can go directly along that edge between A and B, or we can go from A to C and back to B. That's possible too. And as we've seen, the paths between two given vertices may be different lengths. All right, so now that you've got a sort of a feel for the type of definitions that we have for graphs, go ahead and try to complete that graph terminology set of activities that's on the PDF included with this video.